Okay, so in this lecture, I am going to go over some of the key points about the examination and what I'm trying to achieve in terms of assessment during the exam. So the examination will last 3 hours. It will take place in person at the moment, in person on campus, in an exam hall in January, and the examination is split into 2 parts. The first part is roughly 50% is theory, and you will solve a problem by hand. So in the second part of this session, Omer is going to go over another example of this. Roughly 50% of the exam is testing your understanding of the practice of carrying out finite element analysis. And so in those questions you will you will write answers without mathematics, and you will support those answers with diagrams. All of the questions that you will see inside the examination paper, you must answer. They are all compulsory. So this is not my policy. This is not my decision. This is a school and perhaps a faculty policy, that in an exam paper, all the questions are compulsory. The exam paper itself has been reviewed by my peers, both internally and externally. What does that mean? That means at the beginning of the semester, when we start teaching, I have already written the examination paper, and the exam paper goes to colleagues in the Department of Mechanical Aerospace and Civil Engineering, and they read the examination paper, and then they assess the examination paper, and they have a rubric where they assess the quality of the questions, whether the questions are easy to understand, whether there is a good balance between mathematics, theory, and practice, and whether the examination is fair. So at that stage, I would receive, or lecturers would receive, feedback on their examination paper. Then the exam paper, if maybe there's some corrections sometimes, the exam paper then goes to a professor at another university external to Manchester. And this is called this person is the external examiner. And the external examiner assesses the examination paper in exactly the same way. And the result is that you have a well-balanced examination that is fair and that assesses the intended learning outcomes specified in the course. So if you work through the course, if you've attended the lectures, you've looked at the materials, you've done the coursework, you've done some preparation for the examination, you've looked at some previous exam papers, then the examination is fair and you will do a very good job. Okay? So let's have a look at the theory side. So what I'm expecting you to understand are concepts such as discretization. You may remember right back in the beginning of the course, I talked about how the finite element method takes a continuous variable. So this could be displacement or a load, and then this variable becomes a discrete variable. And so we have an example here. We have an approximation of displacement. The displacement is computed at the nodes in the mesh. Okay, so we have to remember these concepts. Then the mathematical process of converting this continuous variable to a discrete variable is covered in some pre-recorded lectures. I think I gave those in week 2, which covered the mathematical process of carrying out the discretization. So this is not examined, right? So be very clear that the derivation or the conversion of the continuous variable into a discrete variable, those horrible mathematical lectures with lots of integrations and differentiations, that explain the process of why, where we take the continuous variable and where we convert it into a discrete variable, they are not examined. What I wanted to achieve in those lectures is just to communicate that the finite element method has a mathematical basis and it's not magic. So behind the graphical user interface of ANSYS, in the computer program, there is some quite sophisticated mathematics going on. But, as I say here, you need to understand the idea of shape functions, what they are and where the terms come from, and basically this links into the idea of the P refinement that we looked at in the week 2 assessment 1. So another thing that I want you to, that you should have a look at is common element types. And again, this is covered in one of the early lectures. Could you sketch the main element types? So 1D, 2D, and 3D elements. Do you know what are the degrees of freedom on each of these element types? And are you able to annotate a sketch and show these? So I think in some of the previous papers, exam papers, there are examples of this. A mistake in previous years, I don't think I've seen it in this year's group, is the attempt to constrain rotations in the software package when the element doesn't have rotations. So 1D elements have degrees of freedom that are translations, so movements in X, Y, and Z. And they also have rotational degrees of freedom about, each of the axes. And 3D elements do not have these rotations, and 2D elements typically don't have these rotations either. So this is an important area. The next area is mesh generation. So do you understand how joining elements together, creates a mesh? What do we do with the nodes that are on two elements that are then joined together? Are you able to define all of these different terms, mesh bias, P refinement, H refinement? Do you understand what each of these are used for? And if you had a question in the exam asking something like, how could the solution to this particular problem be improved? Maybe, the answer is to use mesh bias, P refinement, or H refinement, and explain why those techniques could improve the solution. And again, you've covered this in the practical work. Do you know how symmetry might be used to simplify a model? So I think we covered this in the assessment 1. So the last question in assessment 1 was about how the model could be simplified further. Many groups talked about using symmetry. Those groups that didn't talk about using symmetry, in the feedback that I gave, I explained that you could also divide the beam in half and only model half of the beam. And then there are these two other concepts, plane strain and plane stress, which are two-dimensional representations or simplifications of a three-dimensional problem. So these are other concepts that you should definitely know about. So the next thing is boundary conditions. Could are you able to, create a sketch of a finite element model and add boundary conditions to show the loads? Remember, boundary conditions are both the loads and the constraints. So again, this was something that I wanted you to do in assessment 2. And then, in terms of a hand calculation, how do you translate those boundary conditions that are on a sketch of a model to this system of equations? So we've got K, remember, is the stiffness matrix. You've got U, which is the unknown displacements, and F, which are the externally applied loads, the loads that are applied as part of the boundary conditions. Another area that we talked about was converting a distributed load, so a continuous load, into a discrete form, and we used the language equivalent nodal loads. So remember, in the discrete world of finite elements, we can only apply forces at the nodes, but in real life, our load may be distributed over an area. We talked in probably, I think, week 3 about how the equivalent nodal loads are calculated using some of the complicated mathematics, the integrations using the shape functions, and I said that I didn't expect you to learn how to do that, and so this is not assessed in the examination. And what I said was I would like you to learn the equivalent nodal loads for the main element types, and in the in the lecture slides I put little like symbols next to the ones that I said that you needed to learn. Why do I want you to learn them instead of giving you a sheet of equations in the examination? It's very important to be aware, or if you're going to continue with finite element analysis, it's very important to have this concept in the front of your mind. One year an external examiner from structural engineering said that I'd made a mistake in one of the exam questions, and he didn't understand the concept of equivalent nodal loads. And he said, well, in my university, we just divide the load by the number of elements. And, in the lecture, I've shown that doesn't work, and that could give incorrect answers to a finite element calculation. It's very unlikely that any engineer is going to remember just to look up what the equivalent nodal loads are for a particular element. So I want you to have this in the front of your mind, that this is an important area where mistakes can be made, and so you can have a big error in the computed answer to an engineering problem. So another concept that's tested in the theoretical part is the idea of us assembling elements to create a finite element mesh. So in a lot of the, well, in all of the previous exams, you have been given, or you will have been given, or the students will have been given, the element stiffness matrix. And the question requires the student to assemble the element stiffness matrices into a global stiffness matrix. And again, there's no need in this course for you to learn how to derive the element stiffness matrix yourself. So if you have a look at some of the previous examples, and when Omer goes through one today, we'll reinforce that you're given the element stiffness matrix. And then, well, where do people make mistakes? The key part is what happens when the elements are sharing the nodes. Then in that part, the terms are added from the element stiffness matrices. And then the next part is about solving the system of equations. So we go back to this expression, Ku equals F. So we create a system of equations, apply the restraints or constraints. So we know how to take the constraints and what we have to do in that vector of unknown displacements. So we also should know how to apply the externally applied forces to the vector of externally applied forces. Then we've got, in terms of solving the equation, we've got two steps. One is identifying the reduced system of equations. And so if you look at the way that the marks are rewarded in the exam papers, you get marks for identifying the reduced system of equations. And then you've got this other part, which is solving for the displacement, so working out what the displacements are. And so that involves using, you can use any technique that you're comfortable with. And I think Omer's talked about this in one of the tutorials. So what can you do to prepare? There have been examples given during the course. The questions and answers are provided on blackboards. You have 3 examples from previous examinations. And the other thing to bear in mind is that if I got you to do this for 3-dimensional elements like the tetrahedra or the hexahedron with 20 nodes, you probably need 1 or 2 days to solve a problem like that by hand. So in an examination, it only makes sense to set a question using simple elements. So you may see in the examples that I've given so far, examples of beam elements, rod elements, and spring elements. So if I come out of the sharing at the moment and I go to the web browser, so I'm going to share again now. So can you see the Blackboard page? Yeah. So we've got assessment 1, assessment 2, you know about that. And then on Blackboard, there's past exam papers. So I've got some detail there about the exam papers. So the course code, the unit code, changed from last year from 61059 to 60561. So the exam papers in the previous years that I've put on Blackboard are for 61059, but it's exactly the same. So the examination that you will take, or the course, is exactly the same. The intended learning outcomes, the examination, the solution, the format of the exam is exactly the same. And you've got solutions provided together with the exam paper, and an indication of how I might be marking the exam paper. Okay, so you can have a look. Definitely make sure that you look through these before the exam. You may like to try and, I don't know, take one of the exam papers yourself in the preparation and just see if you can, how well you can answer the questions in like your own mock examination, and then you could answer it yourself in terms of preparation. So let me go back to the sharing. I can. So we'll go back to the PowerPoint slide now. So can you see a big blue slide called with practice? Okay. If you can't, Omar should wave his arms.
It's working.
It's working, right, okay. I'm a long way away to be able to hear. Right, so what I've got here is a series of questions. These are not the exam questions. These are hypothetical questions, just to illustrate how I'm thinking. So this question is, outline how any arbitrary geometry might be turned into a finite element mesh. Right, so how would we do that? So typically in the exam paper with this type of question, there may be 10 marks. So you think, okay, how am I going to get 10 marks? So, okay, so maybe there's 10 points that I need to remember. So the answer may involve very simple statements, nothing very complicated. So you could say, okay, we could use computer-aided design. So we could use a package like SolidWorks, and I remember some of you used other packages in your group project to create the CAD geometry. We talked about that last week. So from your own experience, you can talk about any CAD package that you've used, or you could say that you could use the CAD or the functionality of ANSYS or Abacus or any of the finite element packages for you can do some basic creation of models in there. You could talk about, in a very high level way, about how there are algorithms that fill the space with elements, and these use mathematical approaches that are now commonplace in all the sort of common finite element packages, and that they are built in through the graphical user interface. And then we've got these other three areas, which are imaging using photography, laser, or computed tomography, X-ray computed tomography, which we covered last week. So these are all different ways of taking our engineering problem or simplified engineering problem and creating a finite element mesh. So the next question, again, this is a hypothetical question. This is not a question that is in this year's exam. How would you incorporate the effect of temperature change into an elastic analysis? And so one of the lectures, I think we had two lectures. We had one lecture where I talked about thermomechanical problems, and I showed you that the thermal strains were converted into nodal forces. So we had, and there was an example that I provided from the NAFEMS benchmark, one of the reading materials, or I gave 2 or 3 examples, and one of the examples used a package called Fluent to calculate the temperature or the change in temperature in a headlamp. So a car headlamp, so you have a change in temperature in the car headlamp. And in that reading, it explained that they took the temperature and then they could use ANSYS to do the mechanical analysis. And I showed a very simple term in the lecture that showed that a thermal strain could be converted into a nodal force, and then you calculate a mechanical problem with the external load, as you know, as we've done in hand calculations, and as we've done in all of the examples that we've seen in the practical sessions. So external forces, and then we add another external force, which is due to the change in temperature. And then the analysis is solved in the same way in the elastic problem. So again, what I'm looking for is an explanation as to how this might be carried out. So I'm not looking for any mathematical derivations, but I'm looking for evidence that you've thought about in a high level those two lectures. So there was a lecture on thermomechanical analysis, and then there was also a lecture about the nuclear graphite brick, and showing how, you know, a real example of doing this type of calculation, and also the reading. So this is where the reading comes in. The reading. So those NAFEMS benchmarks, what I'm not expecting you to do, there won't be a question that says, did you read the NAFEMS benchmark article, and can you remember it? There won't be a question like that. The reading is there to help you understand the main concepts from many different points of view, so that you get a real understanding of each of the topics. So then this is another question. So if you remember the pressure cooker, pressure cooker hands-on session, what we were trying to do there is to give you some experience using ANSYS to solve nonlinear problems. So you remember we had boundary nonlinearity, we had material nonlinearity, which was plasticity, and we had geometric nonlinearity, which was the rubber, the stretching of the rubber. So there are also 2 pre-recorded lectures on this about the theory, and what are you expected to remember from those 3 pieces of material in the course? So this is a question that might that might come up. What are the main classes of nonlinear problem that can be solved using the finite element method? So there you go, geometric nonlinearity, material nonlinearity, and boundary nonlinearity. What I need to explain here very carefully is that what I'm expecting is not to see just the words. What I'm expecting to see is a short explanation of what geometric nonlinearity means. So what I've learned in previous years as a lecturer is that sometimes when the students answer the question, they remember my slide from this revision lecture, and if they see this question, what are the main classes of nonlinear problem that can be used solved using the finite element method, they just write geometric nonlinearity, material nonlinearity, boundary nonlinearity, exactly as I've written in this slide. This slide is a note, this is a summary. So if you write what I've written on this slide as an answer to an exam question, whilst it is correct, you would probably only get 3 marks out of 10. Because you need to explain what the terms mean. Okay, so be very careful of that when you're revising. So you would need to say geometric nonlinearity is different to linear analysis because the response of the material involves very large strains, and we need to take into account that elements of the material may undergo rotation and translation as well as deformation. So it's a very, very difficult, very different type of analysis to linear analysis. Material nonlinearity. You wouldn't just write material nonlinearity, you would explain that material nonlinearity means that, I don't know, a typical material, the response of a typical material to loading may involve a number of stages. Firstly, a linear response, then there may be a yield point after which the deformation is irreversible, and if you keep on loading the material beyond yield, eventually you'll reach the ultimate limit state of the material, and then the behavior of the material will start changing to, transitioning from, say, a plastic irreversible behavior to fracture. And then boundary nonlinearity is the process by which we deal with contact between different components in a product or different components in a structure, and their interaction. And explain, so we've got here, explain that there may be different laws of how the material behaves, this type of analysis. So the linear analysis is very fast. And I think I explained in one of the lectures that 90% of engineering analysis is linear, because we don't want our products to fail. We don't want our products to break. So our first iterations of a design are to make sure that the analysis our design, the response of the structure stays in the linear part of the stress strain curve. So that's that area. Another question that I like, and you may see in the previous exam papers are, what are the main sources of uncertainty in an analysis? Okay, so we covered this in a theoretical way early on in the course, and then we had a look at that case study using the nuclear reactors bricks. So basically, this is a very easy question to answer. Very easy, because every single thing that we can think about in terms of specifying our analysis may be uncertain. So the material properties, geometry, loading conditions, everything about our analysis can be uncertain. What can be done to mitigate the effects of uncertainty? So we could carry out a sensitivity analysis, look at the extremes of loading, and this is a philosophy that is embedded in design codes, so limit state analysis and things like this. Or we could embrace the uncertainty and carry out Monte Carlo simulation, so use random variables and look at the reliability of a design rather than a design that is stated to adhere to some particular rules. So we look at, in this case, the probability that the design will, or our structural component will satisfy the requirements that we've specified, in terms of what we're trying to build. Now, again, if you have a question like this, what are the main sources of uncertainty and analysis, and what can be done to mitigate the effects of uncertainty on a design? Please do not just write these individual words and phrases and think that you've answered the question. Because again, if you just write what's on this slide into an answer on your exam paper, you will get 3 marks out of 10. So I want you to explain what each of those means, but not in a very complicated way. 2 or 3 sentences explaining how you might carry out sensitivity analysis. Or 2 or 3 sentences about Monte Carlo simulation. And then it's very easy to get good marks in a question like this. Another question, outline ways in which analysis tools can be used to optimize a design. So here we may go back to the idea of the analysis specification. Identify the objective to be optimized, set up an analysis so that parameters can be altered, and uses an optimization tool that launches many analyses. What computer platforms can be used for simulation? So if you remember, Dr. Peter Boom gave you a lecture about high-performance computing and cloud computing. So the intended learning outcome from that lecture, or the main one, is being able to appreciate the different types of computing platform that you could use as an engineer to carry out finite element analysis, and an understanding of when it is appropriate to use each of those different types of platform. So cloud computing, high performance computing, and desktop computing. Okay, so the next part, and we're getting close to the end now, is how to answer those types of questions. So I'm kind of repeating myself a little bit. So show that you understand the question. So define any terms that are used in the question. This shows that you understand the question. Answer the question fully. So do not just list the keywords. Write full and complete sentences of text that explain what the keyword means and why and how it answers the question. Now, I have to, as a lecturer, I have to try and get the average of the class, the average score for the unit between 57% and 57 and 74%. I have to make sure that the average fits within that range. If the average of the class is less than 57, then the university pushes everybody's score upwards. If the average is above 74%, the university pushes everybody's score downwards. So I have to write an exam that ensures that most students get between 60 and 70. So I have to have a mixture of questions that are fairly straightforward so that everybody in the class is able to answer some easy questions. So to make sure that all the class passes. So around, so the pass mark is 40%. And then I have to have some hard questions that only a small number of the class would be able to answer. So I have to have a mixture of difficulty. Now, you will have seen in my marking of the assessment 1, I'm quite strict in terms of my marking. So I have exactly the same philosophy for the exam. In the exam, it may be possible to get 8 out of 10 for each of those, sort of questions about practice, if you write a very good answer. But I need to keep some marks in reserve for the very best students. So what I do is I reserve 2 out of 10 marks for an answer that uses a real engineering example that shows that the student has read the case studies, or that they've learned something from their own experience, or they've read some other materials about the technique. So in order to get 10 out of 10 for any of the questions that I've gone through just now, you would need a real engineering example to support your answer, as well as answering the question correctly. Now, I have awarded, I think the top mark in the exam since I've been teaching this has been 92 out of 100, and that was a student that referred to the case studies and other real engineering examples in all of their answers. So this is, so if you're interested in being top of the class, the only way of doing that is, to refer to the case studies. And then the last thing is to draw pictures. So I don't mean draw pictures of, your classmate, or what you think the horrible lecturer is like, so these are pictures related to the question. So if you can, support your answer with a picture, this also is a good strategy for getting a good mark. Why is it a good strategy for getting a good mark? If I don't understand your explanation in terms of writing, but you have a diagram, you have a picture that explains what you're trying to communicate to me in your exam paper, maybe I think, okay, I didn't understand the writing, but it is very clear that the student it's very clear that the student understands the concept and has answered the question correctly. So in this class, we've got a large number of students whose English is not their native language. So am I going to penalize poor English? No. Yeah, so don't worry about the quality of your English. Don't worry about that. I'll take that into account, and as I say, if you draw a picture about, to help answer a question, then I will understand. Okay. I think we're coming to an end. Cheating, right? So cheating. Not last year, but the year before, there were 10 people in the class cheated. And we know all of the tricks of cheating. So, what happens if the invigilator, the person that's checking during the exam session, what happens if they see somebody that's cheating? So cheating could be taking some notes with you, or having on your calculator some notes written in the lid of the calculator. So you need to make sure that your calculator doesn't have any notes. It could be, even if you have notes that are not related to the exam, the invigilator will take your paper because they don't know the topic of the examination or whether what you've written on your calculator is going to help you. If you have writing that is in Chinese or German or French or any other language, maybe the invigilator can't read it, but they will assume that the student is cheating. And what they will do is they will let you complete your exam up to the 3 hours, and then they will take your paper. And then what happens is all of the materials and the paper are put in a plastic bag, which is like a police evidence bag, and then I'm given that evidence bag and I have to decide whether the materials in that bag show that the student cheated or not. So sometimes I say, no, this material won't have helped the student and they're okay. But other times, the person caught cheating, the case is referred to like a mini court in the university, and the student is asked to go to the court and then defend the accusation of cheating. And what can happen there is maybe the student would have a mark of 0 for the course unit, or they may be asked to leave the degree program. So this is very serious. So just please be very, very careful not to have any notes, even if they're related to other subjects, written on top of your calculator or any other materials. So in summary, the theory, there's a solution to simple finite element problem by hand. So there's various examples that you're given. The practical aspects are assessed by a number of questions. There will be 5 questions, each with 10 marks each. And the NAFEM's case studies may give you extra insight and understanding and may help you answer some of the questions. So before I hand back over to Omar, I'd like to thank you for your attention and all of your hard work during this semester. I wish you every success in the exam. I'm sure you're all going to do a really good job. And yeah, I hope you have a good break over the holiday and a happy New Year. So that's it. Thank you, Omar, for hosting me. Okay. So I don't know if there are any questions, or whether we just hand over to Omar, and Omar can answer. Omar's very familiar with the course. He could answer any questions, and maybe it's better to use the time to go over the hand calculation. What do you want to do, Omar?
Do anybody have any questions? Lee is here. Nobody is asking what the exam paper will be. You can ask him and see what he says.
So, Omar, could you repeat that question to me if it was a question?
But someone is asking what the exam paper will be. What the exam paper will be.
What it will be?
Yeah. They have started cheating from now on.
Ah, okay. Yeah, okay. If somebody wants to ask me how much does the exam paper cost, I would have understood the joke. Yeah, so how much? Yeah, I don't know. There's 188 students, aren't there? So if it was, I don't know, if it was £500 per student, maybe I could retire. Okay, are we done, Omar?
Yeah, I think so. We are all good.
Okay, so thank you everybody, and stay safe as well. And I'll catch up with you later, Omar. Okay?
Thank you so much, Lee. Certainly, Lee has given you some very, very important tips. Some of them you will realize now, and some of the tips you will realize when you are sitting in the exam. So, it's okay. So, we will carry on with the numerical part now, which is 50% of the exam. I've been doing this tutorial for past 3-4 years, and every year this 50% is like free marks. You know, it's very easy. You don't have to worry about the English. You have been doing mathematics from your high school or even from your elementary level. It's only mathematics, very basic concepts. You just have to keep in mind few things and be careful about certain things. You would be ending up with the right solution. So we will start off with the problem from the very beginning. If you guys have any specific problem that you want me to go through, please let me know. If you think you have a problem from tutorials, we can go and solve with that. Or if you want me to choose a problem and start solving, I'm happy to do that. Or you guys can even say that we want to solve a beam element or a bar element or a rod element. There are two types of element, yes? Do you guys remember? We have covered two types of element. We have beam elements and we have the rod elements, or we call the bar elements. So beam elements have more degrees of freedom. One node will have 2 degrees of freedom, and the rod element will have 1 degree of freedom per node. So they are easy to solve. If you leave it on me, I will go with the rod element. But then if the beam element comes in the exam, you guys would be saying that we did not get any revision for that. Beam element. The more difficult one, would I say, actually they both are easy, but the beam element is, there are more chances of making mathematical mistakes or silly mistakes. So what I'll do is we'll start off with the beam element, and then during this I will be giving you some hints that if it was a rod element, what changes you would be doing. So that will probably help us speed up the process and cover both of them. So I'll be very kind to you guys. Let me connect my. Let me show you the problem. Actually, it's in the tutorial. So if you. Right, so this is the first example. This is the rod element. So that's the rod element. This is how it looks like. Right? You can either have this in your exam or you can have a beam element. And the beam element would look. Oh, you can't see the screen. That's strange. Alright, so let me open it on the blackboard. यार HDMI ते हलण त खपे From the study point of view, you have your past exams, right? You have your past exam, you have your tutorials, you have your case studies. There is bunch of material which is available. If you cover all that, you would be very good in the exam, right? So let me show you the bar element first. Right, so yeah, this is how the bar element looks like. Yes, please. Increase what? Sure. Is it good now? Right, so this is how the bar element looks like. From the structures point of view or from mechanical engineering point of view, this is a rod which can only deform in axial direction. It cannot bend, it cannot twist. It can only elongate and it can only compress. So this is the property of the rod element. Now when I say elongation, you see I am moving my hands only in one direction. And remember the concept of degrees of freedom. You need to understand this concept from the words itself. You don't need to memorize anything. Degrees of freedom. Freedom means possibility to move. And degrees means by how much. How many possibilities are there for something to move? So when I just say this, it's only elongation in one direction along the x-axis or any axis you can say. It can be positive, it can be negative. If it is elongation, it is tension. If it is compression, if it is shortening, we say it is compression. So this is how the rod element looks like. This can be one question in your exam. And then, so this was in January examination 2021. And then in 2020, you had a beam element. So yeah, a very complicated beam element. If I was giving this exam, I wouldn't feel lucky, to be honest. Because it's a beam element, and then on the top of that it has 3 elements. So complexity over complexity, right? So let's go step by step and crack the code for these problems and see how they are solved, right? Just before we begin, what level of understanding are you guys standing? Do you want me to solve it by hand over here, or do you want me to go through the solution? Well, if you make me do the hard work, then you have to give me the numbers. I will not run the calculator, right? You give me the numbers and I will put it down. Is that a deal? No? Okay, you don't have more options. Right. All right, so right. So I think this works. So on one side we have the problem on the screen over here, and then on this side I'll be writing down. Yes, it works. And all right, so let's do it together now. So we would be going a little bit quick because we don't want to make you guys wait longer than the time. So the first question, so this is a beam element given over here. So you can assume this as a typical beam. By looking at the problem, guys, can I have your attention please, all of you? Right? So we are about to solve a 50 points problem. So these are straight away 50 marks. I want you to get very good at this after this session, and don't want to spend time, near the exam. You can prepare for other things. You can have this part covered in this session only. Right? So do solve it with me. You all have to do it a couple of times with your hand. If you like it or not, to get a good practice on it. So do it with me, and then we would be on the same pace. So just by looking at the question, we have a beam element. It is divided into 3 elements, and 3 elements means 4 nodes, yeah, because every element has 2 nodes. So that's something that I can directly figure out just by looking at the figure. And then we are given the modulus of elasticity, which is 210 exponent 9 Pascal, and then inertia. And then it has been discretized using 3 beam finite elements. Element 2 is subjected to a uniformly distributed load of 7,000 Newton meter. The length of each beam is indicated. The vertical degrees of freedom are constrained in all the nodes. So vertical degrees of freedom are constrained, right? So it cannot move. The nodes cannot move in the vertical direction. You know, for example, if you have a roller support, if you have a support like this, we say that the support will give a vertical reaction. In other words, it will not allow something to move in the vertical direction, right? If you have a pin support, then you have a reaction in vertical direction and horizontal direction. And then if you have a fixed support, then you have a vertical reaction, a horizontal reaction, and a rotation. So a fixed support will have a 0 degrees of freedom, a pin support will have 1 degrees of freedom, and a roller support will have 2 degrees of freedom, right? So it's the opposite of the number of reactions, right? Degree of freedom will be 2, degree of freedom would be 1, and degrees of freedom would be 0 for this one. So this is just a very, very quick recap of what the properties of the support conditions are. We will need this thing later in the step, right? So let's move on to part A. Determine the equivalent nodal loads acting on the beam, right? We have to determine equivalent nodal loads. Remember that the whole point of finite element is that we break the body into small, small elements, and then these elements are connected by nodes. And the forces, the loads that we have, they are always acting on the nodes. A load cannot act on an element. That's not possible. That's not the way finite element has been designed. So if you see over here, on element number 2, we have a uniformly distributed load W that is distributed on the element. If you want to solve this problem, we have to distribute this load onto the nodes, right? Yeah, so that's the first thing. Another variation that you can have in this problem was, for example, if you have a beam like this, for example, if it was like this, and instead of a uniformly distributed load, you had 2 point loads, right? Then you don't have to do anything, right? So don't get confused. This is the final stage. This is the final stage that you want to achieve, distributing the uniformly load as a nodal loads. I do repeat myself so that people can catch up with me. I know some of you are very, very good, but let's do it as a teamwork. And then another variation you can have in this problem is that you have a load like this, right? So a variably distributed load across the element. The intensity of the load is changing as we move along the length of the element. So if you have a load like this, again that needs to be converted into equivalent point load. Now the question is, how do we convert them, right? Now in one of the lectures, I think it's lecture number 2 or something like this, in which you were taught different elements, and beside each element you have that heart symbol or the star symbol showing that these elements are important. Now that was the purpose of those elements, that they were telling you that if it is a beam element with a uniformly distributed load, what would be the distribution on the nodes? If it was a rod element, what would be the distribution on the node? If it was a 2D element, what would be the distribution on the node, right? So make sure to go to that lecture and be very, very clear about that, right? So the problem that we have in this case is we have a beam, right? Determine the equivalent nodal load. So see, there are 4 marks, and now we will solve this problem, and you will see that how simple it is, right? it has a uniformly distributed load. Right? And what is the intensity? 7,000 Newton meter. Right? It says determine the equivalent nodal forces or the nodal loads. Now, we have to find out the nodal loads on all the nodes, right? So what would be the load on node number 1, node number 2, node number 3, and so on, right? So, let me label the nodes over here. Node 1, node 2, node 3, and node 4, right? And this is the element 1, 2, 3. And we know that, now again, this is coming from knowledge of the theory, that every node of the beam element will have 2 degrees of freedom, right? We have a vertical degrees of freedom and we have a rotation. Right, for all the nodes. So I will call this as U1, V1, U2, V2, U3, V3, U4, and V4. Yes, please.
Does it not say that all degrees of freedom are constrained enough for?
Sorry?
Like the last sentence of the question.
Yeah.
Why would we still join them?
No, we are just setting up the problem right now. Right? Coming to the first part. Right? Coming to the first part now. So on node, so how do you distribute a uniformly distributed load onto the nodes? In beam elements, how do you distribute the load? Any idea, guys? So remember, if it was a point load, if it was a point load, then you don't have to do anything. You just directly write the matrix. Let me write down the matrix that I am talking about so that things are more clearer to you. So I will say P2, P is a symbol that I am using to donate nodes. I can see over here that one node has 2 degrees of freedom, right? And we have to distribute the load of the element on the nodes. And one element has 2 nodes, right? And each node has 2 degrees of freedom. So altogether, we need 4 forces. Right? Does it make sense? Yeah? Following me? The load has to be distributed on nodes. One element has 2 nodes, and per node we have 2 forces, a moment and a vertical force. So it has to be a column matrix of 4 elements. So I will write U2, V2, U3, V3, right? Does it make sense? Right, now coming back to the values, what would be the values? Now, just to give you a recap, the load is always distributed by half, right? The load is always distributed by half. So if this is 7,000 newtons per meter, so I'll convert this into a point load. 7,000 into L, what is the length of this element? 5 meters. 7,000 into 5, right? So that's the total load on the element. And what is this value? 35,000, right? And the load is always distributed as half-half, right? So per element would be divide by 2, right? So it should be how much? 35,000 divided by 2 is how much? 17,500. 17,500 and 17,500, right? Is this correct? Why? Huh? Yes, exactly. They should come over here. Right, so just testing you guys if you are awake. I often make these mistakes intentionally to teach you the wrong thing. So, is this correct now? Is this correct now? What did I miss? A negative sign. Someone said negative sign. Why do we have a negative sign? Yes. Yes, it's a different direction to the sign convention. The standard sign convention is pointing upwards, but the force is acting downwards. So our direction should be, the sign should be negative, right? So that's the place to fill up for the forces. Now what about the moments? If you have a uniformly distributed load, how do we calculate the end moments? Structural engineers, it should be a piece of cake for you. Yes, that's correct. Now it doesn't matter. It's your sign convention. That the point is that it should be in the right place in the matrix. It's always displacements, moments, displacement, moments, displacement, moments. I can switch the symbols, it doesn't matter. I realize this after putting this down. Right, so how do we calculate the end moments? If you have a uniformly distributed load, the end moments, right, if you have a system like this, and if I want to convert this into an equivalent system of end moments, if I want to convert this into this, the values for moments are always WL square upon 12. Do you recall this? Right? So whenever we convert a uniformly distributed load, it results in forces, vertical forces, as well as end moments. Right? And similarly with a variably distributed load, whenever you convert that into an equivalent nodal forces, they result in some moments and some point loads. Now, for a uniformly distributed load, we said that it is half-half, but it's not half-half for a variably distributed load. For a triangular load, it's different. So you have to see this in lecture number 2. What are the values? And similarly, the moments for this one is WL square upon 12. If it was a triangular load, these values will change. So bear this in mind and keep all these case studies, these different options in your mind when you go for the exam, right? So WL square upon 12, if you do the simple mathematics, W is 7,000, L is 5, and 12 is 12. So what would be the value? 14583. Right, and similarly over here. One four five eight three. So is this correct now? Which one? Yes, please.
Shouldn't the minus 17,500 equal the base of the U?
Which one, sorry?
The 17,500.
Yeah.
The B values of the U values.
Yes, it depends. It depends on the symbol that you are using. I think this is causing confusion. It doesn't matter, but let's do this. Right? What's important is the position of the matrix, the position in the matrix. You always have to put the vertical force, then the moment. The vertical force, then the moment. It can be A, B, C, D, it can be E, F, G, it can be anything. It's the position, that's what's important. Right? Now, we got the numbers, now we need to look at the sign again. So for the first one, what would be the sign? It should be, sorry? Yes, the moment should be negative, but which one? Both of them, just one? Second one should be negative. Why is that? Because this is clockwise and standard sign convention is anti-clockwise. Yeah, so that's perfect. So this is all that you had to do in this problem, and you are good to get 4 marks. Right? So we have done this very, very slowly, but when you are prepared for the exam and when you have enough practice, this will hardly take 5 minutes or maybe less than that. Right? So let's move on to the next part. Draw the boundary conditions on a sketch of the beam. Right? Now this is again a very, very important question covered in the theory. You have to draw the boundary conditions. Whenever the problem says the boundary conditions, you have to include the constraints and you have to include the forces. Right? If you show the constraints and if you show the forces, your sketch of boundary conditions is complete. And then you have to label it properly as well. Show the node numbering, show the element numbering. So we have already done this part over here. Right, this one. So we have shown all the forces, the direction of the forces and the forces that are acting, and the elements as well. So even those are shown. Right? So is this correct? It has everything. Yes, please.
In that diagram, we have shown the direction or rotation of the movement in the same direction.
Which one?
For this diagram,
Yeah.
we have shown the direction of the movement in the same direction for all these.
Also, it's the standard is, yeah, it's always like this. Let me draw the moments again. Right, nobody is pointing my mistakes. Thank you so much. So like this. Right? These are the directions of the moment, and then accordingly you can see for the sign conventions. Now, is this sketch correct for the boundary condition? Read the question. What was the question? the vertical degrees of freedom are constrained, right, in all nodes. So in the diagram that I am showing, I am not constraining anything. I am showing that there is degree of freedom everywhere. So this diagram is incorrect, right? What would be the correct version of the diagram? So you have a pin, you have a roller support over here, a roller support over here, a roller support over here. And let's see if we have something on node 4. All degrees of freedom are constrained in node 4, right? So on node 4, when it says all degrees of freedom are constrained, it means there is a fixed support, right? Now I have drawn the constraints. Now I need to show the forces, right? And then in the previous part, we just calculated the forces. Right, and what were the values? 17500, and this is right. Now this is the correct diagram. So we are showing the boundary conditions and we are showing the forces. So the two conditions are fulfilled. You get your another 4 marks. Right? In some of the problem, it always says, yes, please.
How do we know which way to draw the moments from?
So you have to look for the standard sign convention, right? What is the standard sign convention for the beam elements? Anybody remembers the standard sign convention for beam elements? Let's see in I think both of them are clockwise. Does anybody have the lectures? Does anybody have the lectures? See, what are the standard sign conventions? Open lecture number 2. I think it's in the next one. Which problem was that? Let's see this one. Maybe it's this one. Yes, it's this one.
Let's look at
So see, this is the rod element and this is the standard sign convention, right? So a finite element problem has standard sign convention, right? So for a rod element, it is like this. And this is how the sign conventions are for the beam element. So it's anti-clockwise, right? Now this is the standard sign convention, right? If your calculated direction is opposite to what we have over here, then we say it's negative, right? So if you look at in our solution, we have drawn one anti-clockwise and one clockwise, right? And if you go back, and let me show you the fixed end moments as well. How do fixed end moments look like? That will clear the picture even further. Fixed and moments. See, so this is what we have calculated. The WL square upon 12 formula, it gives you moments in these directions. So this one is anti-clockwise, right? And according to the normal sign convention, this was anti-clockwise as well. So we say this would be positive, right? And for this one, this is clockwise, and the conventional sign over here was anti-clockwise. So we say that this moment is negative, right? That is why if you see over here, we have a negative sign over here and a positive sign over here. And at this stage, it doesn't really matter what sign you choose, what direction you draw, because the mathematics need to be correct, right? Okay, so let's go back to the question now. So everybody clear with these 4 marks? How to draw the boundary conditions? There are 2 key things, constraints and the loads. And then write out the element connectivity matrix. Okay, what is the element connectivity matrix? Anybody? This is the most easiest thing. Element connectivity matrix is how the elements are connected. So you have to draw 2 columns, element and then node I and then node J, right? So 3 columns, we have 3 elements. One, 2, 3. So I will simply write 1, 2, 3 over here, and then this is node 1, node 2, node 3, and node 4, right? So on element number 1, we have node 1 and node 2, right? On element number 2, what nodes do we have? 2, 2 and 3. And on element number 3 we have 3 and 4. So there you go, that's your matrix, right? Very simple and straightforward. So you get 8 and 3, 11 marks over here, right? So if you guys are well prepared, and if you are doing it by your own and well prepared, well practiced for the exam, you will hardly take 10 minutes to reach this stage if you don't make any mistakes. So the advice is to go slowly, because you will have plenty of the time in the exam. Go slowly, be careful about the direction, the minus signs, because this is where you will make mistakes, probably not with the concepts. Using the expression for the beam element stiffness matrix given in equation 1, calculate 3 element stiffness matrices, right? So this is a standard element stiffness matrix. For each element, we have 3 elements. So you will have 3 element shiftless matrices, right? And what would be the change in each of them? You have a variable length L over here. We can see that length of each of the element is different, right? EI should be, I think it's same. Yeah, EI is same for all the elements. Sometimes if they want to really play with your mathematical side of the brain, they will change EI as well. But Lee has never done that since past 5 years, so he wouldn't be doing that. So you need to make simply 3 element shiftless matrices. This is a very simple and straightforward.